Hi, my name is Christian Hilario and I'm here because ayos namin to, so hindi pwedeng hindi mo kasi hindi ka graduate. Charot lang. I'm here because I'm going to talk about the theory of relativity by Albert Einstein. So if you want to learn something, you make sure that you keep on watching. So, the theory of relativity by Mr. Albert Einstein is composed of 5 parts. First is the classical relativity. Second is time dilation. Third is length contraction. Fourth is time travel. And the last one is general theory of relativity. So the first part of this theory is the classical relativity, which directly states that there is no such thing as absolute motion and absolute rest, because objects move relatively with each other. So, for you to understand furthermore, here is an example.
Look at the truck with 2 kids playing catch. The truck is moving at a constant speed of 50 miles per hour, but as the kids are also moving with it at 50 miles per hour, they could easily think that they are standing still. When the children throw the ball at 10 miles per hour, they observe that the ball they have thrown is moving at 10 miles per hour. But their little brother, who is not on the truck and is standing still, has observed that the ball has moved at 60 miles per hour. He has added both the speed of the truck and the speed of the ball together. But is the little brother really standing still? No. The Earth is constantly in motion, the Sun is constantly in motion, and the galaxy is constantly in motion. Therefore, nothing is ever at absolute rest or absolute motion. Things just move relative to each other. This is classical relativity.
So the next part of this theory is the time dilation. Here's an example.
So, let's imagine a beam of light being reflected between 2 mirrors. Let's replicate this setup so we have another beam of light being reflected between another set of mirrors, but this time the mirrors are moving close to the speed of light. We can see in the moving set of mirrors that the beam of light is moving a greater distance. Now, let's put a couple of people into this scenario. Meet Alex. He sits inside the moving set of mirrors, and Bill sits inside the stationary set of mirrors. The speed of light must be the same for both Alex and Bill, and their light beams must hit the bottom mirror after the same amount of time has passed. But, as Alex's light beam is covering a longer distance, how is that possible? Well,
as you know, speed is equal to distance over time. Since Alex has a greater distance, he will require more time than Bill. Actually, Alex's 1 minute turns out to be longer than Bill's 1 minute when compared. Time has slowed down for Alex. This is called time dilation. Okay, the third part of this theory is the length contraction. As we mentioned, the greater the distance, the greater the time. However, they don't increase in the same amount. In fact, time doesn't dilate enough to account for the speed to remain the same for the boys. And this is where the length contraction comes. Here is an example.
When objects are moving close to the speed of light, not only does time slow down, but the object itself contracts. This is called length contraction. So in this scenario, Alex and his mirrors are actually smaller than we thought, and therefore the distance the light beam has to travel is actually smaller than we thought also.
So in conclusion, time dilation and length contraction works together to ensure that the speed of light remains the same for the two of them. Okay, to the next part of this theory, which is the general theory of relativity. Here is a short example of this part.
Einstein realized that the special theory of relativity, which we explained previously, only worked for circumstances when things moved at constant speeds through the universe. What about when objects sped up? What about the effect of gravity? And come to think of it, what is gravitational pull after all? Einstein theorized that objects warped space-time around it, causing it to become curved, and as a result, objects experience gravitational attraction to each other. This warping of space-time explains how objects behave as they move through space. This is the general theory of relativity.
So, on to the next part of the theory, which is time travel. Time slows down for all objects traveling close to the speed of light, and time stops when it travels at the same speed of light. Therefore, time must go backwards if the object traveling is faster than the speed of light. So, as you might ask me, how would I know if this is true? To debunk that, here is a simple explanation of this chapter.
How do we know that the theory of relativity is true? Well, countless experiments have been carried out and Einstein's equations hold true. Modern GPS uses Einstein's theory of relativity to pinpoint our locations with impressive accuracy. In 1971, an experiment was conducted with 4 super-accurate atomic clocks, which were set to the exact same time as a reference clock. The clocks were placed aboard commercial flights and the planes flew twice around the world, first eastward and then westward. When the clocks returned and were compared to the reference clock, the clocks were no longer all synchronized, and the differences were consistent with the predictions of special and general relativity.
And that will be all for this video. I hope you learned something and I hope you liked it as much as I had fun filming this. And don't forget to subscribe to my main channel and follow me on all my social media accounts like Instagram, Facebook, and Snapchat. Thank you. Bye!